Hello everyone, welcome back to the last part of the aliphatic nucleophilic substitution reaction. So we already have discussed the two major mechanisms which are SN1, SN2. Then we have discussed their dependence on solvent purity and then leaving group, the substrate. We discuss all these possible effects that we could see in the rate of reaction. Today we're going to discuss SNI, which is substitution nucleophilic intramolecular or internal specifically. So internal. So basically what it says is a part of the leaving group. So let me take the pointer here. So a part of the leaving group must be able to attach the substrate after detaching it from the leaving group. So basically in initial stage, one of the like a part of the leaving group will detach, and then that will act as a nucleophile in the uh, like the final state. So as for example, when we react the alcohol with the thionyl chloride, so first the OH lone pair will attach to the sulfur that leads to the release of HCl, and then you can see that there may be a formation of cationic and anionic species, because this is very like a stable carbanion. And then what would happen, that chloride will attack on the chlorine atom, so you get RCl and you get the sulfur dioxide. Okay, so this is basically that you can see the chloride, which was a leaving group at one point, that can act as a nucleophile. So here I have shown you that this chloride is coming back, but the HCl minus, that Cl minus, that can also act as a nucleophile over here. So I can say that Cl minus can attack over there, then this bond will form a sulfur oxygen double bond and Cl minus comes out. Okay, so this is basically uh, the kind of a situation where the part of the leaving group can act as a nucleophile in the final state to give us the product. Okay. Now, very important thing is that in most of the cases we retain the chirality. Okay, and the reason is being that this is coming from the nucleophile, the leaving group itself. So because the leaving group present in the same site, so the chloride will transfer from the same site. Okay, so that is the reason why the retention of chirality will be always maintained in this particular reaction. Okay, so in other case, we could have, if you can perform this reaction in presence of nucleophilic catalyst. Okay, we already discussed in one of our video that pyridine can act as a nucleophilic catalyst. So once you form the first compound after replacing one of the Cl minus, then the pyridine can attack over there. Then this chloride will come out. Okay, then chloride will be attacked over there to the R. Then this will be release of the SO2 gas as well as the pyridine. Now here, because the chloride is coming from the backside, we will have inversion of chirality. So there are two different way the reaction could happen. So if you don't perform the reaction if you do perform the reaction in absence of the catalyst, you get the retention of chirality. But if you do in presence of chirality, you can have a inversion of chirality. Okay, the reason is that in absence of catalyst, the nucleophile is coming from the same side where the leaving group is detaching from the molecule or the carbon center. In the other case, that chloride or the nucleophile is coming from the back side of the leaving group. So that is the reason why in one case you get that inversion of chirality, in other case you get the retention of chirality. Okay, so next topic is neighboring group participation, or it is also known as enchimeric assistance. There are a few important observations that the different scientists have found is that this consists an unshared pair of electrons or a double bond, the beta to the leaving group. So basically, either you could have a heteroatom or you could have a double bond or unsaturation, which is beta to the leaving group. The reaction rate is always greater than the expected. So the reaction always is to be like if you perform the SN1 reaction or SN2 reaction, if you can predict the reaction mechanism, it is found that it is always much higher than the normal SN1 SN2 mechanism reaction rates. Consists essentially of two SN2 substitutions. So basically there are two steps of SN2 mechanism happen. I will show you the mechanism one by one, that it will be very useful. And the rate is unimolecular. That is very much important. You understand that how it is unimolecular. Okay, and in this case there will be always a retention of chirality. That is a very interesting thing, because if it is unimolecular, we have to learn that this is the SN1 mechanism. And if it is SN1 mechanism, you have a racemization theoretically, but as I told earlier that you may have always inversion to some extent, because your before that that leaving group departs the molecule completely, the nucleophile start coming from the backside. Okay, so that is why you always see some sort of like inversion in excess rather than complete racemization. Okay. Now I'm going to discuss two examples taking on cyclohexane. This is a very beautiful system, and if you really see the examples, most of the proof coming from proof for the like enantioselective reactions or any chiral center reaction is mainly done in this particular cyclohexane system, because you can log the stereochemistry. Okay, and that is very much important to define the chirality, and you can because there is no point of racemization rotation, you fix the framework in any cyclic system. Okay, and that will ease many things to explain. Okay, so let's take an example. So you have a trans acetate, so one acetate, one tosylate, and you do the acidolysis using acetic acid as a solvent, and you can see that in this case you have you can obtain the products, a mixture of products which basically trans to each other. So you start with the trans isomer and you end up with two different trans isomers. Now basically they are enantiomers. The thing is that you can see here we have above the plane, here we have above the plane, but in this case we see the below the plane. In the other case this is below the plane, this is below the plane, this is above the plane, but more or less the stereochemistry between the two carbon centers are always trans. On the other hand, if you start with two the two substituents on the cis position, so for example here tosylate above the plane and the acetate above the plane, you end up with the trans isomer. Now how can you explain this? Okay, and it is found that this compound react very fast, or the reaction rate is much faster compared to the cis isomer. So to explain this, so we have to use another concept which is for neighboring group participation. So if you see the particular mechanism over here, what you can see that this is a particular trans isomer. I start with this and I can draw it in the chair form. Now in the chair form, so I have to take diaxial, because the substituents are basically very small in size. They can go in the diaxial form, which is unstable compared to the both equatorial. Obviously that is true, but the reaction will be much more feasible in the equatorial position. Now you can see here in the diaxial form, the lone pair from this particular oxygen can easily find the anti-bonding of the carbon-oxygen bond over there, and then there will be intramolecular nucleophilic attack via SN2 mechanism. Okay, and you produce a strain unstable cationic species or intermediate, which will be highly unstable. Okay, then that acetate ion will attack either over there or over there. Okay, so you can get two different isomers over there. Okay, now if you can just rearrange this to, like, if you can draw this structure cyclohexane chair form into the cyclohexane normal planar form, you can see that both are remain anti to each other. So that is what we can easily explain, that how this reaction happening and why the rate of the reaction is much faster, because this is happening intramolecularly, and because this is the this is that RDS, or the slowest step of the reaction. So this reaction is unimolecular reaction. Okay, so it mainly retain the chirality. Okay. Now here In the other isomer, what happens, you see, if you take the cis isomer, where you can have one equatorial, one axial. Now this is far away because the anti-bonding is always in this side, and you can rotate this to bring this one over there, but the anti-bonding is this side, so attack should happen from that side, but this is far away from this particular acetate, and that is the reason the reaction does not occur or proceed via NGP. It is normal SN2 reaction. Okay, and that is the reason why this reaction is much slower compared to this particular reaction. Okay, so I guess I able to understand to explain some of this NGP with some example. I will give you some few more example over here. For example, if you have this particular compound, so I already mentioned about that heteroatom, or you could have a carboxyl. I just explained in the previous slide. So not carboxyl, it was the particularly your ester. Now this is a ketone there. You can have a acetate, you can have any aromatic ring, you can have a NH, NHR. Sulfur is very known, iodide or yeah, I minus, Br minus, Cl minus. Those things, if you have there, not sorry, one thing I should mention here, that this is not a minus I. It cannot be minus because it's already attached to the carbon center. So iodide is there. Sorry, I'm stating again the wrong thing. It should be iodine, bromine, or chlorine. Okay, not iodide, because when it attached to the carbon center, it should be neutral. So that is my mistake. So basically, you can see here particular example. So you have a Br and you have the OH. Okay. Now if you add HBr, you are adding acids. What acid will do? This will protonate the OH, and then this Br lone pair will attack to the anti-bonding of the carbon-oxygen bond. Okay. Then you produce a cyclic bromonium ion, and this is very much unstable. And then nucleophilic attack could happen, and you can get two different carbons. Okay, but they are still anti to each other. That is one of the thing. And the second example is with the aromatic ring. You can see, so you have a tosyl group over here. So this is the beta position double bond. So this is the alpha and the beta double bond is there. So this double bond can actually attack to the carbon oxygen bond from the anti position or in the antibonding orbital of the carbon oxygen bond, and then you could have a cyclic like intermediate. So I have shown some resonance structure of this, but at the end this acetate will attack from to the either of the carbon, and you get only one bond, because if it attacks over there, this bond will open, so you get terminal. When this can attack, then this bond will open, so you will get the terminal. So always you will get the terminal carbon, which is this part. Okay, but this reaction, you can say that this is the kind of SN1 or SN2 mechanism. So acetate is not a good nucleophile, so SN2 is not a very good preferable mechanism, which is also sterically hindered. At the same time, that SN1 is favorable, but because of this, because of the presence of this aromatic ring, the reaction proceed via neighboring group participation or NGP, or you can also say Ankermanic effect. Okay, this is another beautiful example I'm going to discuss over here. So you start with this particular example. You have a tosylate, so tosylate will be a leaving group. Okay, and then you can see here you have a methyl group next to the methoxy group. Okay, then I can draw this in a particular conformation, because this oxygen lone pair now it is available to attack the anti-bonding of the carbon oxygen bond, and then you can get the product over here. So you can see here this tosylate is now simply replaced with the acetate. That is a normal product, but another product is that the acetate is attached to the to this position. Okay, so this is very much interesting here, because you see that methyl group seems to be marked over there. It is not like that. I will show you that the mechanism finally, then you can understand the same. If you take another isomer, okay, if you take another isomer, so here you can see the OTS was away from this methoxy. Okay, this methyl. Now you can see the methyl is close to the OTS. Okay, so you can say here it is a primary tosylate group, and here we have a secondary tosylate. This is another word you can see like this. You can also rearrange this molecule, this particular conformation, and you can attack the oxygen lone pair can attack from this side, and you can have a similar product. Interestingly, what it was observed that you can start either from this isomer or this isomer, you always end up with the mixture of 60-40 these two compounds. How this is possible? Okay, the possible way is this one. In both the cases, this is the common intermediate. Okay, what is the common intermediate? That oxygen attack over there, and you get this particular compound. And this case as well, oxygen attack over there, and you get this particular compound. So this is the intermediate. Now, acetate can attack over there or attack over there. So the one which attack over there, that is sterically less hindered, so you get 60% product. This is sterically more hindered, so you got 40% product. So basically, to explain the product formation from these two isomers, okay. Now, thing is that if the reaction would proceed via SN1 or SN2 mechanism, if it is SN2 mechanism, for example, if you consider here, so this should be the product, and that is the expected product. This is not expected at all. And if you see this one, from here we should get this product, we should not get this one, but you get the mixture of these two, and this can only be explained by following or using the neighboring group participation mechanism. Okay, so that is very interesting example. Okay, so in both the cases you got 60-40 isomers. Okay, so this we can wind up our substitution reaction, nucleophilic substitution reaction in the aliphatic molecule. So I have given some of the examples that order the anions according to the nucleophilicity and explain. So what would be the order for this one? So basically that this should be the more nucleophilic, because the reason is that nucleophilicity always depends on the donation of the electron. So more easily it can donate, better the nucleophilic is, unless until there is some other effect like a steric crowding is there. Okay, so basically among these two, so this is less electronegative. Oxygen is the second most electronegative element on the periodic table. So what will happen? So this should be better. And among these two, because OR, so R is electron donating group, so this should be better nucleophile compared to this one. Okay, but if the R is very bulky, so the nucleophilicity will be reduced. So if you think about this, you can rationalize with the example of Williamson ether synthesis. Okay, so that you can just correlate with that example. You can easily understand what is that. Among these, which will be the better nucleophile? So tertiary butoxide, ethoxide, and the OH. So ethoxide will be better because tertiary butoxide have a huge sterically counting, so that should be less. Okay, and after this you can get this one, then finally you can get this one. So this is very simple. So this is second example is that you can draw the mechanism. Okay, and what is the particular mechanism you can mention? So basically it is NGP. So you have a thiol which can attack over there. Okay, and then the methanol will attack from the other side. So you have retention of chirality if you have a chiral center. Unfortunately, I did not draw, did not keep any chiral center. So it is NGP. So the sulfur will be participating in the reaction. You find the possible products in the following compounds. So basically, this is again ankymanic effect. Okay, so this will be attacking. So you get from both the cases, you're supposed to get the similar product ratio. Okay, so that is one of the example. So one very important example, probably I already discussed here. These two compounds are not neither good for SN1 mechanism nor good for SN2 mechanism. The reason is that SN2 mechanism from backside it is hindered because of this particular tertiary butyl group. SN1 is also impossible because this is the primary carbocation. So that is impossible for both SN1 and SN2. So this case SN2 backside is highly hindered, so SN2 is not possible. SN1, this is bridgehead position, so carbocation is unstable. So you cannot have, you cannot stabilize the prime carbocation over there. So basically, these two compounds will not stabilize the carbocation. So SN1 is not possible. Backside is highly hindered, so SN2 is not possible. Okay. So this I will wind up the whole topic of aliphatic nucleophilic substitution reaction. Later on, I will post other videos related to the organic chemistry. Thank you.